Okay, guys, do you listen me? Or do you think I have to use the microphone? Now? But um, do you know if someone else will join or okay? But there are any problems, conflict with other lessons? So let's start. So today we will see some exercise regarding the lecture that the Professor Crovetti made this week, in particular regarding electrical characteristics of digital gate. This is the first exercise lesson, and since you said that maybe on Tuesday you have more conflict with another lab, we will do all the exercise on Friday. So the first exercise that we will see is regarding the gates compatibility. In reference to the datasheet reported below, the output of these gates, this is a code, universal code that you can find a particular component on a website if you have to see the datasheet, if you have to buy it. This is an AND and operates at a VDD equal to 4.5 volt and is connected to the input of a similar gate operated at the same power supply voltage. Assume that no current is drawn from the output and that VOH is more or less equal to VDD and VOL is more or less equal to 0 volt. Here I reported you the data sheet of the component, and we will see it together. As you can see in the data sheet is reported the VCC, which is the supply voltage. In the data sheet, everything is clearly specified so that you can't misunderstand nothing. And in this case, VCC is our VDD, because I told you that the gates operated at VDD equal to 4.5. So if you have, if we have 4.5 volt, here we have to find the VCC equal to 4.5 volt. And in this case, for VIH is this row. Maybe wait a minute. We'll see here the row where VCC is equal to 4.5 to 5.5, which means that if you have a power voltage supply of 4.5 to 5.5 volt, you have to see these two values here. In case you have a VDD equal to 2 volts or other values, you can see other specific here, which tells you which value of VIH use in case the different power voltage supply. If there are values only limits at 5.5 volt, means that the gates cannot have a power voltage supply higher than 5.5 volt. This is the maximum voltage that the gates can use. The same things is done for the other characteristics, in this case VIL, VU high, VU low, and so on. I suppose that in the lessons you should have seen the meaning of voltage output high and voltage output low. Am I right? During the lesson, it has been explained what VOH and VOL are. Can you tell me yes or no? It's been seen? Okay, perfect. Just brief recap. If a gate operates, for example, this is an AND, no? If I told you that VOH is equal to VDD, means that these gates will communicate one if the voltage supplied to it is higher than, in this case, 4.5 volt. In this case, it will read 1. Here is 1, here is 0. If we have voltage OL, means that the voltage, since that the gate will send 0, must be lower than 0 volt. Okay? So, in this case, we can go on and see what the exercise asks. So, are the electrical levels of the two gates compatible? If the answer is yes, calculate the noise margin M0 and M1 at the low and high logic level. So, as I told you before, VU output at the high level must be equal to VDD, and the VU output low level must be equal to 0 volt. These are specific that the exercise will tell you, or that you can in some way retrieve from the datasheet that is given to you. As the exercise explain, we have the first NAND, which is linked, the output is linked to the input of the second NAND. They are equal, they are of the both family, so they have the same characteristic. Moreover, they are operated in the same range of power supply, which is 4.5 volt, 4.5 volt. So, if we are at the high level, means that this NAND must send 1 to the second door, right? To the second gates. But what's the condition since the second gates can read 1? If VOH communicates the high output level to the VIH of the second gate must be less than OH from the data that you can read from the datasheet. If the gate 1 send 1 to the second one, this is the VOH that we have to see. But in the second gates, what we have to see, since the input must read 1, is VIH, because we are at the high level. So let's see from the data sheet how to retrieve the value. Yes, please. Okay, there are different types of gates, but in any case, here we are simplifying just the scheme, the circuit, to make you understand how this kind of compatibility must be seen. Okay, let's assume that, for example, to one of the n input of the gates, there is one gate, and on the other input, there are other gates, or assume that other inputs are always linked with the same gates, and so that this criteria must be always seen. This is the general rule, the general mindset to use if you have to understand the compatibility of two gates. Did you understand now? Fine. Please, of course, ask me if I'm not clear. Other misunderstanding or something not clear? Okay. So I told you that VOH of the output of the first gate is given because it's VDD. And now we have to retrieve the value input at the I level of the second gate, which assume, guess what, is the same of this, no? Because the gates are equal. But now, see just this, VIH. Let's go before, see the data sheet. VIH, so is this. I told you that we must see in V of 5.5 of VCC, so we have to use this formula, right? So go on. We do VCC for 0.7. The answer is this one. And so the rule that we have to use here is that VIH must be lower than VOH. Because guess what? If it's higher, if the VIH is higher than this, it can't read 1. It's 0 for it. So in this case, we have 3.15 volt and 4.5 volt. And so it's minor, and the compatibility is okay. On the second end, we have the low level. At the low level, we are talking about voltage output low that communicates to, at the low level, an output of 0 to this, right? Zero, VO, I, because it's an input, and it's low. So the second input must be big. So the VIL of the second gate must be bigger than VOL. And even in this case, VIL is retrieved from the datasheet. So now let's see in the datasheet that in the datasheet VIL must be seen always regarding the voltage supply, which is in this case the same 4.5. And here the datasheet gives you the formula VCC for 0.3. So go on. The value is 1.35 volt. And in this case, the rule is that the voltage input level of the second gate must be bigger than voltage output level, because if not, they will not see properly the zero input. So this is respected, so there is compatibility. If we want to calculate the noise margin at the low level, we have to use the input low and the voltage output low, which in this case is equal to 1.35. In the I noise margin, we have to use the I level. So output high, input high. And we have the same, 1.35 volt. Is it clear in this first case, or there are any doubt? Because all the other tasks are more or less similar. Okay, so let's go on. And the second task is repeat point A in case in which the first gate operates at a VDD 4.5 and the second gate operates at 2 volt. So what we will change in this case? We will change the value of voltage input I and voltage input low that we have to retrieve from the datasheet, right? And since in this case we have modified the voltage supply applied to the gate, here is still 4.5, but here is 2 volts. So let's see on the data sheet. If voltage I is 2 volt, we have to use 1.5. If voltage input low is 2 volt, we have to use 0.5. So remember these two values and using it in to see the condition. In this case, 1.5 volt is minor than 4.5 volt because the first gate is the same. So the condition is respected. In the low level, 0.5 is still major than 0 volt. So even in this case, the condition is respected and the two gates are compatible. If we want to calculate the noise margin, again, in the low level, we have input minor output, and this is 0.5. In the I level, we have output I, input I, and this is 3 volts. If the noise margin are major than 0, they are fine. Now let's go on with the third task, which is repeat point A for the case in which first gate output operates at 2 volts and the second gate input operates at 3.5 volt. So now things are changes. And see what happens. If here we have 2 volt, we have to use the same value that we have used before. And here we have 3.5. So we have to manage different values that we have to retrieve to the datasheet. In this case, input 2 of the second gate is given in a condition of power supply 3.5. So let's see from the datasheet. 3.5 is here. And we still have the same formula, VCC multiplied 0.7. So 3.5 or 0.7 is 2.45. And here we have 2 volt because the voltage output at the high level still remains equal to VDD. But in the first gate, we have changing it to 2 volts. So in this case, we have 2.45, which is minor than 2 volts. No, that's not. So this condition is not respected. And if it's not respected only in one level, which can be high or low, the gates are not compatible. Not compatible at all, even if the low level is compatible. In fact, just for clearance, let's see at the low level what happened. We have again 3.5, and we have to see the voltage input at the low level. Let's see it from the datasheet. It's here, and we have VCC multiplied 0.3, which is equal to 1.05. And it's bigger than 0 volt. So in this case, is respected. There are no problem at the low level, but still remains problem here. In fact, if we go to calculate the noise margin at the low level, it's fine, is major than 0. At the high level, is minor than 0, and this is not acceptable. That's clear? Okay. So now let's see what we can do in this case. And we go to the last task. If in any of the above cases, A, C, the electrical levels of the two gates are not compatible, propose a solution to properly interface the two circuits and calculate the noise margin for the proposed solution. So, in our case, only the C requests something between them to make the two gates compatible. And we can use a level shifter. As the name will suggest you, shift the voltage so that can be compatible to the second gates. So, if there are now 3 gates, we have to see the compatibility between the one and the middle, between the middle and the second. So now the conditions are double. If these are respected, all the circuits can work fine. So, if we introduce a level shifter of the same family, which operates at 2.5, we have to see the voltage input and output low and high always from the datasheet because it's of the same family. And the voltage supply applied to it is 2.5. So, first of all, let's see if here at the eye level, the first gate and the level shifter are compatible. We have to use a VCC for 0.7. Is it right? Let's see. For the value 2.5. We'll go to the datasheet. 2.5 is here, and we have, in fact, VCC multiplied 0.7. Here we have the same, and we have VCC multiplied to 0.3. So let's do our calculation. And in this case, for the eye level, 2.5 for 0.7 is 1.75, which is minor than 2 volt. So is respected. Even for the second gates, so now we are here, this is 1, this is 2, we are always at the eye level. Voltage of the input at the eye is given for 0.7 up to 3.5. This is equal to the last case, and it's minor, so it's fine. Let's see now at the low level. Here we see that we have to do for 0.3 and it's 0.75. So 0.75 is major than 0 volt, so that's fine. Now see in the second case, it's as before, we have plus multiplied to 0.3, which is major than 0 volt, so is correct. Too fast? Again, here we can calculate the noise margin, and the noise margin at the low level are input minus output, which is 1.05. In the high level, we have output minus input, which is 0.05 volt. Is very little, but that's fine. There is now compatibility between these two gates thanks to the level shifter, which is just a simple another NAND door applied between them, which operates in a middle case, which can make the two gates compatible. Okay, there are problems here? Yes, please. Okay, in this case, I will tell you what happened. Happened that at the first time, we put values randomly, and we see that there wasn't compatibility. So in this case, we adjust the the power supply voltage, since that there was compatibility with the two gates. It's something that is assigned to you. If you have to make the things working well, you have to adjust the value so that the compatibility is respected. The voltage supply is accepted by the gates. There are all these rules that must be taken into account, so that in this case, your aim was to make the two doors working together, and so that you designed the working of the level shifter. It's up to you.
What VDD works with the shifter. We could find the correct interval algebraically, right?
If you don't know,
If you we could solve it algebraically.
yes, if you don't know it, but I told you that the level shifter is of the same family of the other two doors, so you know how it works. Because in the datasheet, all the values are given. If you see the datasheet, you can decide which VCCs or VDD use to make things working. That's exactly what we have done when we proposed the exercise, to make the things working. Okay? Any other question? No? Okay. Give me a minute, so I want to just see if in the, okay, here. From the web, there are any problems? You can see everything? I don't know. See the chart. I guess no problem. Okay. So now let's move on to the second exercise, which is a little bit on the another level of the first. For a digital output, is it not specified which? VU output at the high level is 3.3 volt, and voltage output low is 0 volt. And the output resistance at the high state is 5 kilo ohm. At the low state, the resistance is 10 kilo ohm. The output of the gates drives three gates, which input capacitance is 1 picofarad, through an interconnect characterized by a capacitance of 2 picofarad. Evaluate the rise-fall time and the high to low, low to high propagation delay, TPHL and TPLH. So when there is a task and it's not given the circuit, try to think and imagine which is the schematic behind it. So it said that a voltage, that a digital output is connected to something. So in this case, I have designed an inverter, but it could be everything you want, even just a block which inside has these two resistance. And then the output is connected to three gates. So as you mentioned before, there are more inputs to an end, right? In this case, we have just linked to one input here. The other, it's not given and can be connected to everything else. But in the real case, there are capacitance to take into account. There is an input capacitance for each gate, and there is also a capacitance for the wire which connects the gates. So, how we can evaluate the rise and fall times and the propagation delay? These two resistance, it is clear why they are here, because here we should imagine that if this is an inverter, which is the representation of the inverter with the P and NMOS? The same that we saw the last time. We have this, we have the PMOS, and the NMOS. Did you remember? And here we have the output. And this is put here. So if this works in the real lives, we have interactors, as we mentioned the last time, right? And if we have interactors, we have also resistance. And in this case, here, we have the resistance at the I level, which is the resistance I for the PMOS, which will give you the output 1. And this is the resistance low of the NMOS, which will give you the low level. These two resistance has to be taken into account if we are considering a real case. So let's see how it works. Rise and fall times and propagation delay. Okay. So during the lectures, the professor should tell you that the rise and the fall time are the value between in the rise time, the voltage applied, the timing to arrive at the 90% of the final voltage minus the timing to arriving at 10% of the voltage is the rise time. The fall time is the opposite, and for the propagation delay, we have the value assumed when VDD, when the voltage arrived to the half or VDD, right? This is familiar to you? Okay. To derive the simple formula, we have to use the first order RC transition analysis, which is nevertheless this equation. So in this case, I derived it to you. And let's see. For the propagation delay, we have that the voltage must arrive at the half of VDD. So we have 0.5 VDD, and the equation still remains the same. So VDD can be simplified. We can pass through the logarithm. And at the end, with the trivial algebra, we can arrive at the formula. If we go to low to high, we have to use Ri. Vegetables. Okay. If we have to go to high to low, we have to use R low. Let's do the same with the rise and fall time. In the first case, we have to calculate 0.9 VDD, and in the second case, 0.1 VDD. Let's do the same trivial algebra solution to arrive in this case. For example, time rise is T9 to minus T10. So with trivial algebra, we arrive to this formula, which is the logarithm of 9 RH LL CL. We already have the resistance, but there is something that it's missing, which is CL. Which is CL? Is the total capacitance that the gate see in the output, which is also called load capacitance, because it's just a load in this case. And how is calculated? So we say that we have 3 gates plus the wire. So 3 multiplied the capacitance of the input gates, and then we add also the wire for a total of 5 picofarad. We can apply this simple formula to calculate the timing of 4, but it can be asked to derive this formula. Is it clear how it has been derived? Or there are any troubles with this formula? Okay, I guess it's fine. If you don't remember them, just derivative them. You use always the same equation, which is Vt equal to V multiplied 1 minus Rc. And then you can derive everything you want, applying the condition here to Vt, which can be V alpha or 0.1 volt or 0.1 volt and so on. Okay? Go through this and then you can derive every formula of the timing delay and timing. Okay? So we can move on to the exercise 3. And in this case, we have another step to do, which is the waveform. In this case, we have already this circuit, and this circuit has been done by the exercise. And we have to evaluate the waveform of A, B, and C, and the output here of the internal logical signal ABC in case the gates are ideal, so there is no timing delay, and in case each gate brings you a delay. In this case, in the real case, evaluate the minimum and the maximum propagation delay. Okay? So now let's see step by step. The variation of the input is given by the exercise and is this. So as you can see, x1, x2, and x3 has this waveform. Based to this waveform, we have to understand how A, B, and C, and of course the output, can be. So let's see the ideal case. Do you want to do this from the beginning or you want to see already done? From the beginning? Okay, fine. So let's put another page. Perfect. Okay. I'm apologizing for my drawing, but I will do my best. So let's see x1 and x2 first. You have to take okay, let's see this circuit, okay? It's complex. We have to divide it in more sub-problems. So in the first case, understand A. A is given by just one end, and it's given by x1 and x2. So let's see how x1 and x2 are made. We have x1 here, and then x2, which starts more or less from the half. So It's something, maybe we can change color. It's something that goes like this. And x2 is something that goes like this. Right? Yes, more or less. Okay, so we have this. Here there is a changing from x1. Here there is a changing for x2. Here there is a changing for x1. And here there is a changing for x2. Let's see the front where they are changing. Okay, to understand how the input will change. So here, let's see how A will be. I suggest you to proceed in this way so that it's more clear. Let's do step by step and see the NAND is 1 in all cases and 0 if in the case we have 1 and 1. So we have x1, x2. We have 0, 0, 0, 1, 1, 0, 1, 1. And A is equal to 1 in all cases, except here, right? So let's see what happened. 0, 0, 1. There. Okay, let's make it red. We have 1. Then there is a changing. 1, 0 is still 1. Then we have 1, another changing. 1, 1 is 0, so down. Until the last changing, not the last, but here there is another changing, so we have 0 and 1, so again 1. And then we have the last changing, which is 0 and 0, which is again 1. And this is the wave. Clear? Okay. So it goes something like this. And now we have to see the second problem, which is B. B is given by x2 and x3. x3 is something more similar to x1. Okay, let's do it again. So maybe divided it in this way. Another page. Okay. So here for B, we have to see x2 and x3, right? x2 and x3, and it's an OR. Okay, so x2 is equal to before. So we have something like this. Then we have x3, which is more similar to this. Yeah, more or less. So we have again 1 changing, 2 changing, 2 changing, 3. Here another one. So 1, 2, and 3, right? And let's see what happened to B. B in this case is given by the OR. And what's the OR? Is 0 just if it's 0 and 0, and then always 1. So 0, 0, x2, x1, x3, and then B. Right? So let's see what happened. 0, 0 still remains 0. Let's do over. Okay. 0. Then there is a changing here. We have 0 and 1, which is 1. Then there is another changing. 1 and 0 still remains 1. Then another changing, and we have 0 and 0, which is 0. So this is B. Okay? Okay. So now we have done A, we have done B, there is C. C in this case is given by A and B. So we simply take the output of that we have already done, A and B, and let's put it on the page. Let's put it here. We have C, A, and B. So let's see before how is made the B. A is 1, then 0, and then 1, 1. 1, 1, 0, again 1, right? Yes. And then we have B, which is 0, 1, 1, 0. One, 1, 0. I don't know if the timing are fine. You can see it here. Okay, here we have A, B, and C. So we have 1, 1, 1, 0. If I can copy and paste, I would like to. Of course not. So let's assume just to understand this, and then we will see in this case. Here there is another NAND. So we have again always 1 and then 0. So 1 and 0 is 1. 1 and 0 is 1. Then we have, I think that this is must be done more or less here. But if we have 0 and 1, we have again 1, and then so on. So let's see in the real case, here we have 1 and 0, and so we have 1. Then there is a changing here, not here, there is a change here, and we have 0, because it's 1, 1, 0. Then we have a changing here, and we have 0 and 1, which is again 1. Then we have a changing here, and so is 1 and 1, 0. And then we have a changing here, so 0 and 1, 1. It's clear? Okay. Now the last cases, we have to take as input of the NAND, the last NAND, C and B, and we have the output. Let's see it here, just because if I draw it from the beginning, I make a mistake. And we have, there is an NAND, so we have 0 and 1, 1. Then let's see where there is the switch of the input. So here and here, we have 1 and 0, so 1. Then there is a changing just here, 1, 1, 0. Then there is a changing just here, so we have 0 and 1, 1. And then we have another changing both here and here, and we have 0 and 1, 1. And this is epsilon. Okay, so now this is the ideal case. I didn't give you any delay, but if we see the real case, we obtain something like this, which is a little bit tricky, because we have to consider the delay that each output has due to the gate and apply it to the waveform. So let's start again from the beginning, taking into account gates by gates. The first gate is the NAND, and we have to see the A. How is the A? It's given by x1 and x2. So in this case, we have to consider just the delay of one gate, which is the NAND. And this NAND has a delay of 2 nanoseconds. So if we have taken already the output before, we can just take them and translate it of 2 nanoseconds. As you can see here. Maybe yellow because I didn't use it. Okay, so x1, x2. x1, x2, x1, x2. There are this transition. Let's see where the front changing. Here there is a 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 changing. So in this case, 0, 0 is 1, and that's fine. 1 and 0 is 1, and that's fine. Here we have the changing of the output, because we have 1 and 1, which is 0. But in this case, since the transition has a delay of 2 nanoseconds given by the gate, the transition of the output will be done 2 nanoseconds later. So we have to translate it of 2 nanoseconds. The same is done in the second transition, which is given here, because we have 1 and 0, and so we have again 1, and here the transition is given 2 nanoseconds later. It's clear? The same thing is done for the other gates. Even for B, we have the input as input x2 and x3. So let's see what happened. For x2 and x3, we have a changing here. We have a changing here and here, and we have a changing here. Okay. This will give you a transition, the first changing. And this changing must be delayed of which time? The time of delay of the door, of the gates. And the gates of the OR is 1 nanosecond. So the delay that we have to report here is 1 nanosecond. to be coherent in the whole graph, let's try to use a delay which is less than the first, so more or less the half. So here there is the switching, and the switching is dilated of 1 nanosecond. Again, here there is a transition, but this transition does give you a transition in the output because it's always 1. Again, here is always 1. In the last transition, we have the transition of the output from 1 to 0, and we have to dilated it of still 1 nanosecond. Clear? Okay. Now, in the same way, let's see what happened. For the last case, C. For C, we have to take an A and B. So here there is a transition. Here there is the transition of A. Here there is a transition of A. And here there is a transition of B. But which transition makes a changing in C? Is this transition here, then gives a transition here. There is a transition here, here, and here. So now, to see the delay, if the transition is made by B, how much delay will be here? 1 nanosecond, because it's given by the OR, B. Then we have the transition here, and is given by the A, and the A is given by 2. And then we have the transition here, and the same here, just delayed. But in this case, we have to add also the second end of C. So here we have to consider the delay of the B, so the OR, the delay of the A, so the end, and the delay of C, which is another end. So we have 2 NAND. Here, I mean, that's state. It's 2. And so the total delay here is 1 plus 2 nanoseconds. Here is a delay made by the NAND. So 2 plus 2, so 4 nanoseconds. Here there is a delay given by this, so 1 plus 2 nanoseconds, right? Because the transition is made by B, so 1 nanosecond, plus the delay of the NAND door of C, which make a transition, we have 3 nanosecond as here. 3 nanosecond, 4 nanosecond, 3 nanosecond. Clear? Yeah. Yes. We have 5 if the transition is made by 1, by A, so NAND, by B, so OR, and we have 3, and C. So if the transition is made by both the signals, we have 3 nanoseconds of transition plus the NAND of C, and it's 5 nanoseconds, right? But if the transition is made by just one of the 2 signals, we have to consider just the delay of the door of the gates, which the signal caused the transition. Okay? Because if nothing is changing here, there is no delay. It's not changing. So 5 nanoseconds is in the maximum case. At the end, we have the final output, which follow the same rules. And so here, let's clear a little bit and do again the
3 plus the gap of the.
Exactly. Let's think that this is 3. This is 4, right? And this is 3 again.
Yeah, 3
Red plus is blue plus 1, which is similar to this, but it's the delay of this NAND. Okay, so let's do it again for the last output so that maybe it's better to understand. Yeah. Okay.
I agree to the.
Okay. So you say if all these 3 cause a delay of 5, why just we not consider 5 of delay for both, for all of them? Yes. Yes.
Delay second logic gate.
And that's what we are doing.
But is it 5 and 4?
5 is the maximum. Maximum if this cause a changing, this cause a changing. In this case, we have not a case where both the input cause a changing here. So we have to consider, in this case, there is a changing here, which is due to B, right? So we have 1 nanosecond of delay, and then the delay of the gates that will gives you C. So it's 3, as we mentioned before. In this case, the transition is given by A, no? Because B still remains 1. So we have 2 nanoseconds plus the delay of C, right? And it's 4. Here, tell me, which is the delay? 4. Okay? In the last case? Okay, 3. If A is 1. Yeah.
Shouldn't we consider the second delay is higher than just that one? Because
Okay. I understand. Because you're saying that if the delay happens in the same time, you have just to consider the higher. Yes, that's true, but it depends of the changing. Because if it's changing and this not, we have to consider the delay of what is changing. Okay, so it depends. If they are changing both together, yes, happen what you say. Okay, perfect. Yeah. After the red changes, here you say we should have 4. Yes, and C shouldn't changes. The last NAND needs time to gives you C. So return. Here you said I wrote 4, okay? Yes, but this cannot go in the same times as he was saying, because To obtain the changing of A, you have to wait 2 nanoseconds, okay? And then you have to pass A to this NAND. And then to have C, you have to wait another 2 nanoseconds. So it's 4.
That's it.
But okay, you mean just in the graph? Oh, yes, in the graph, yes. Yes. In the graph here, this is 2, yes. Yes. I was saying the total, okay? Yes, you're right. Okay. Fine. Any other question? Okay. So let's do it again, the same logic for the last one. Okay, so in the last one, we have to consider B and C, right? The changing is here, then we have a changing here, then we have a changing here, then we have a changing here, right? Okay, now let's see which caused the transition. Both of them cause the transition, right? Here, this does not change, so this caused the transition. This caused the transition, and both of them does not cause nothing. Because the output still remains the same, right? Do you agree? Okay. So here, there is no transition, so no delay. Here there is a transition of these two inputs, but the output does not have a transition, so that's fine. Here, we have a transition caused by the green, so C. And the delay of C was 4, total of 4. But here we have another NAND, so the total delay is 6, right? Where is the no. Here there is another transition. The transition is made by C. Here we have the same transition of 4 plus 2 of the other NAND. We have 6. And then still remains the same. Clear? Okay. Let's move on. Okay, wait a minute. Is it everything clear here for the delay? Perfect. So now the last task. It says, in the real case, let's find the critical path that will gives you the higher delay. What do you have to do here? You have to look at the circuits and try to draw the longer path. So go go through the gates and see how much gates you can collect and how much is the delay that you can collect, and then find the shorter path. So the most critical is the longer. And in this case, if you look at the circuit, which is the longer path that you can draw? Is the one that goes through the 3 NAND, because they have the much delay, the higher delay, and they are 3. So the total delay is 6 nanoseconds. The shorter path is the one that goes from the OR to the NAND, to the last NAND. There are 2 only gates, and one is an OR, which is just 1 nanosecond of delay, and the NAND has 2 nanoseconds, for a total of 3 nanoseconds. We have to find the path that goes from the input to the output, the longer and the shorter. Do you find any path here? Any other? X2, X2B, C1. Okay, so you're telling me this, right? It's not? No. Let's calculate the delay. Which is the delay? 1 or, so 1. Then one end, and it's 2. And then the second end is 5 nanoseconds. It's not critical. It's not the shorter. It's just a path. Okay. Do you find anything else? No. Okay. So, did you agree with me that this is the longer and the green is the shorter? Okay. Now let's go to the last exercise. What time is it? Sorry. Okay. We have 10 minutes, so short. Okay. We have the same NAND door that we have before and operates at 2.3 volt and voltage supply, which with reference to the same data sheet that this is the continue of the data sheet of before. We have to calculate the minimum resistance that can be connected to the output of the NAND and the output and 0 volt, so the ground. This just means ground. So that to have a minimum guaranteed voltage output H min of 2 volts. And then suppose that the output is to be connected to the input of gates of a different family that absorbs 100 microampere at the low state and 200 microampere at the high state. How many gates this kind of gates can be connected to the output to have a minimum guaranteed voltage output I min of 2 volts? Let's see. So the first task is the minimum resistance. When there are no specification, the minimum resistance that you can connect to the output, to the ground, is just the load, as we talked before regarding the capacitance. So here we have the resistance, the load resistance, and the load resistance is this one. And we want to know the value, since that the minimum output H voltage is 2, and this is given by the exercise. Now, to go through, we have to see the current that this gates gives you as output in the I level. So let's see to the data sheet. We have to see here, we have voltage I, output I, and we find here the voltage supply, which is 2.3, and let's see which is the current. The current is minus 2 milliampere. Minus 2 milliampere does not mean that we have a value of minus 2. The minus is just the sense of the current, which goes out, okay? Does not mean that there is minus 2. It's just 2. So, minus indicates the sense of the current. Now, we have to calculate the minimum value of the load resistance. And if which is the current that goes through this? Is the current that we have already evaluated from the data sheet, so 2 milliampere. If you want that this 2 milliampere, and this is 2 volt, the output current must be minor than 2 milliampere. Yeah. Is I or H? No, I don't understand. What do you mean? Yes. Okay. IOH is just is just the current that goes through them. But here, that can be also other stuffs. So there is a total current. In this case, we want just to consider if we put a resistance, which is the value of this resistance, so that the total current is minor than IOH, which is determined by the gate. Okay. So if must be minor, that's 2 milliampere, and the voltage here must be 2 volts, we can consider that the resistance load must be major than this ratio. So the voltage output H min and the current output H max. So the minimum value of the resistance load is 1 kilo. Clear? Now, at the low stage, of course, there is no voltage because it's zero. And so at the end, there are calculations that we can do. In the last task, we have just to see, as we mentioned before, we have here a total current that can go out. And so how many gates we can put here so that we can respect the I output H max, sorry. So we just do in the I level stage, the absorbed current, which is 200 microampere, and the 2 milliampere of the EOH max. So we do iteration, and there is 10 gates. This is the maximum number of gates that we can put here, so that the total current respect the condition of the current output H of the device, of the gates. At the low level, we can also make the calculation that the 2 milliampere divided by the current absorbed by the gates at the low level is 20. But since we have to consider that this works together, meanwhile, we have to take the minimum. So 10 gates is the value of maximum gates that we can apply to the output. Fine. Any question? Take always the minimum condition. Because if we put 20 in the I level, the condition is not respected. Okay, guys, for today is done. If there are any doubts or requests or explanation, please write me or ask me, contact me in any case. And now let's do the second term.